The last session we solved is a puzzle using two heuristics. One was the misplaced tiles, and also we did it using the Manhattan distance. So just a quick review, and then I'm going to, because I received several requests to do the puzzle also using a star search, and then we'll do that example too. So we talked about the heuristic, so here, if you remember, we said that a star search returns optimal solution if it is admissible, so the heuristic that we use is admissible, and also it should be consistent. We mentioned what admissibility and consistency means, so you need to know these two conditions. So the admissibility means that you never actually overestimate, right? So for example, if your actual cost to the goal, which we call it H star of node n, for example, is let's say 10, then your heuristic should always underestimate this amount, right? Because we want to make sure that we want to find the optimal solution. So your heuristic is always less than, for example, 10 in that case. And so this is the how you were checking for admissibility, and then also consistency. So I may ask you, for example, give you a graph and asking you to do these checks. And so for consistency, we mentioned we want to make sure that if you are, for example, considering consistency for node, let's say N1 to the goal, right, it means that your heuristic or estimated cost from node N1 to the goal, that is the estimated cost, right, H of n or N1, node 1, is always less than or equal to if you go from another adjacent node, such as N2, to the goal. So for example, if you wanted to check for consistency of node A, I told you you have to check whether heuristic of A, which is given here, which is 50, right? This should be less than or equal to the sum of estimated cost from node 2, which here is C, right? What is that? That amount is 50, right? Plus the cost from A to C. So you want to make sure if you go from A to goal, it costs less than if you go, for example, A, B, and then to the goal, right? And so this is another condition. So that is what you have to check for each node, and then it should satisfy for all of them. In this case, the admissibility was already satisfied for all the nodes, but the problem was with the consistency condition, right? For node B, what is HB? What is the estimated cost from node B to the goal, or heuristic of B? That is given, right? So you can just check the table, and so that is 200, right? So you have to check that this 200, this amount here, is less than or equal to the cost from B to D, which is 100. Why B to D? Because D is the adjacent node, right? Cost from B to D plus heuristic of D. Heuristic of D is estimated cost from D to the goal, right? So we want to make sure that the cost of going from B to G is estimated cost is less than if you go to, for example, B to the adjacent node B and then to the goal, which didn't satisfy, right? And what does that mean? It means that we were misled by actually expanding A first before B, while our actually optimal paths were in that branch, right? So that is why it didn't, for example, give us the optimal solution. And so we, I assume we know, by now we know why heuristic matters, right? Because it helps us to actually find or prioritizing the path that reaches to the goal like more quickly. And so here we are, and we said, how are we going, for example, to find the heuristic? So one way is to relaxing the problem. What does that mean, relaxing the problem? We just remove some of the constraint, and having like less constraint meaning like the relaxing the problem. Now, in the context of the 8-puzzle example, it could be like, for example, you say we can move from A to B if A is next to B. That is one, for example of the rule. Or, for example, you say I will go A to B only if, for example, B is blank. Or just the most relaxed one, you can move in any direction. Now we solved it, the 8-puzzle using misplaced tiles and Manhattan distance. So in this one, the heuristic is just the number of the tiles that are not in their correct place, right? So I will give you a goal state and initial state. And then I give you, okay, having this initial state and this goal state, then you have to, for example, solve the 8-puzzle using any heuristic that I ask. For example, if it is misplaced tiles, then you use the number of misplaced tiles as your heuristic function. And if it is Manhattan distance, then you use Manhattan distance as heuristic. And this one is very simple, but as I mentioned, the problem is that it doesn't consider the cost of moving like the tiles. That means that it's not the same if, for example, you put them in any order. Maybe it's, for example, if your correct position here, if 7 is here, then the distance is 3. If 7 is here, then the distance is 2, right? But they are not the same. So that is the problem with misplaced tile heuristic. But the good thing is that it's very simple, but not accurate. And then we also discuss Manhattan distance. So what I just explained, in this case, then you consider the sum of the horizontal and vertical moves, right? So, and before I just review the example, reviewing a dominating heuristic, I also explained that if you have, for example, 2 or more heuristic, how do you decide which one is the dominating one? The one that is greater, right? And can you explain why? For example, if we have heuristic 2 and heuristic 1, we say heuristic 2 is dominating heuristic if H2 is greater than or equal to H1. Yeah.
Heuristic 2 is closer to the actual.
Yeah, because H of n, so all the heuristics are, so heuristic means the estimated cost to the goal, right? And these are always less than or equal to H star, which are the actual cost. So this is your actual cost to goal, and this is estimated cost to goal. Now, let's say your heuristic is, let's say, 8. This should be something more like 10, right? Otherwise, we cannot say that's optimal, right? That was also what we had for admissibility. Now, let's say you have 2 heuristics. For example, one is with misplaced tiles, the other one is with Manhattan distance, or any other heuristics that you have. So you have 2 heuristics here. So 2 estimated costs. So if heuristic 1, let's say, is 7, and heuristic 2 is 8, okay? So which one is a better one? The one that is bigger, right? Because it is closer to the actual cost. So that is why H2 is dominating heuristic if it is greater than H1. Now, sorry?
I'm kind of confused. Like, why is that the condition for domination?
Because your actual cost is H star, right? Let's say your actual cost is 10. And then you have 2 heuristic. One is, let's say, 7, one is 8. Which one is better? 8. Why? Because it's a better estimation. It's closer estimation to the actual one. The actual one is 10. So if one heuristic is 5, the other one is, for example, 9. So 9 is a better estimation, right? So if we say cost from, let's say, Toronto to Montreal is, I don't know, 100 kilometers, okay? And then that is the actual cost. your estimation, you have two heuristic. One gives you, for example, 20 kilometers, the other one gives you 90. So the bigger one is more accurate one because it's closer to the actual cost, right? So now, having that in mind, we also solved a puzzle using misplaced tiles and also Manhattan distance. So we said, let's say this is initial state and this is your goal state. What are the number of misplaced tiles here? So 1 is in its correct position, 2 is right, 3 is in the right place. So the only ones are 4, right, 5, and 8. Now, so your heuristic here is 3, right? So at each step, when you want to like expand like each of like these states, you say, okay, how can you move tiles? So you are here in your initial state. What are the number of moves here? 3, right? So you can move in 3 ways. Either you can move 1 down, 7 up, or 4 left, right? Now, if you move 1 down, then you will reach to this state. If you move, for example, 4 to the left, then you reach this state. And then if you move, for example, 7 up, then you reach this state. Now, at each state, you calculate the heuristic, which in this case is number of misplaced tiles, right? Now, what are the number of misplaced tiles here? Always you compare it with your goal state, which is here, right? So the goal state is this one. What are the number of misplaced tiles? So the red ones are the misplaced tiles. The heuristic is 4, and then heuristic is 2, heuristic is 4. And which one do we choose to expand? Always the one with the lower heuristic, right? So we expand this one. And then we say, okay, we can have, because your blank tile is in the middle, then you have 4 ways to move, right? But one of them, like this one, is actually already visited. So if you see, this is equal to this one. So we don't need to like consider it anymore. So we only write these 3. And then here the heuristic is 1. This is when actually you move 5 up, right? This one is if you move 6 left, and this one is if you move 2 down. And then for each of them, you calculate heuristic by calculating the number of misplaced tiles. Here 1, here 3, and here 3, and then you continue the same way. So again, here this one has the lowest heuristic, so you continue to expand this one. And for the next steps, I always ignore the ones that we already visited. So if, for example, you see here we have 3 moves, but I only chose to write these 2 because if you, for example, let's say move 5 down, you reach to the previous state, which we already visited before. So we can only go from 7 to right or 8 to the left, which are here, and then this one is your goal state. And we also used an example of 8 puzzle with Manhattan distance. So in this case, again, we do exactly the same. The only difference is that how you calculating your heuristic. So this time you calculate heuristic by actually summing the Manhattan distance of like all the tiles. So for example, here you can again have like these 3 states. So you can move 1 down or 7 up, or for example 4 to the left to reach to these 3 states. Now, for example, for this one, how do we calculate the heuristic? By you can start, for example, from tile 1. So what is the position, the correct position of tile 1? So comparing to the goal state, which was 1, 2, 3, 4, 5, 6, 7, 8. So this was your goal state, right? So if you see, that is only 1, right? And then for 2 is 0 because it's in the correct position. 3 is in the correct position. And for 4, it's again 1 because 4 should be here, right? So 4 is also 1. 5, what is for 5? Again 1, right? Because 5 should also be here, and so on. And I'm also going to show you one that is has actually the distance more than 1. We don't have anything here, maybe in the next example. So this is another example, again, using Manhattan distance. So for example, because the blank tile here is here, we can have like 3 moves. So one is that if you move 2 to the right, so we reach here. If you move 8, for example, to down, which we reach here, or 7 up, where we reach here. And then for each of them, you calculate the heuristic. For example, for this one, 1 is in the correct place. How about 2? What is the distance of 2 to its goal state? The goal state is this one. What is the distance of 2? Yep, 2, because 2 should be here, right? And then what is the Manhattan distance? The sum of horizontal and vertical moves. You cannot go diagonally. So you can go like up, 1 up, plus 1 left, then it's 2. And what about 3? 3, right? So 3 should be here. So what are the number of moves? Either you move this way, like 1 right, 1 up, which is 3, or 1 up and then 2 right, which is again 3. And then the same way you calculate the heuristic for all the tiles in each state to calculate the total star heuristic, and you choose the one that has the lowest one. So we choose this one to expand. So in the next slide, you see, for example, this node that I'm going to expand. So this is the node that we decided to expand because it had the lowest heuristic. From here, we again can have like 3 moves. One gives us this state if you move 2 to the right. If you move 7 up, you reach here. And then if you move 8 down, you reach here. Again, you calculate heuristic for all of them, right? By just summing the Manhattan distance for all the tiles. And then you choose, for example, this one because it has the lowest heuristic. And from here, we could only, like, how many moves we can have from this one? 1 or 2? Whenever it's in the corner, we can have 2 moves, right? So we can move 8 up or 5 right. And if you move, for example, 8 up, it will like be the same as here. We already visited, so we don't write it again. And then we only can move, for example, 5 to the right, which is this one. And we continue until, so this one, because had more number of tiles that were misplaced, is actually a long example if you want to continue. So I did it up to here. And whenever you reach a goal, we have an example with the A star search today that have, for example, the same heuristic, then you expand all of them, okay? Now, let's do example of a puzzle using A star search. So how did we calculate the cost with using the A star? Yeah, so we consider not only the estimated cost from the node that you are now, from your current state to the goal, but also the actual cost that you had from the starting point to here, right? So now you have your goal state here and your initial state here. So do we have any volunteer to do it, to do the A star search for this one? What if I give you a bonus mark? So every time we have to negotiate how much. Like, you know what is my limit, right? My estimation is always less than or equal to 0.0001. So, but if you we have a lot of opportunities in this class. If you add them, you'll reach to maybe 1% someday. If you're really active. So do we have anyone? I can help you. You are. Yeah, sure. Okay. So, what is how many moves we have here from the initial state?
3.
Right, we have 3. So we can move 6 down, 7 right, or 5 to the left. So we have these 3, right? And then so we can just explain.
search. I take that real quick, but 6 is 1 move away, 1 is 1 move away.
So this edge of 4 here was we calculated before, so you are calculating for this one now, or this one? So okay, for the initial state, the heuristic is calculating the Manhattan distance for each tile, right? So you correctly said, for example, 2 is 1 plus 8 is, for example, 2, right? And then you calculate it for all the tiles. For example, 3 is 0 because it's in the correct position. So just for your convenience, I mark the ones that are misplaced with red because the other ones are already in their correct position, so their heuristic is, so their distance is 0, right? So for 3, 4, 5, 7, the distance is 0. So if you want to calculate, it will be only 2 that is displaced by 1. I always start from the first, the tile 1, so we can do in any order. For example, tile 1, so this is how it looks right now, 2, 8, 3, 1, 6, 4, and 7, 5, right? Which ones are misplaced? 2 is misplaced, 8 is misplaced, 1 is misplaced, 6 is misplaced, 3, 4, 5, 7 are in the correct position, right? You always compare with your goal state, so whatever the goal state is. Now, if you want to use, for example, heuristic using misplaced tiles, you say, okay, the total number of tiles that are misplaced. But now we are using Manhattan distance, so you have to calculate heuristic in this way. That is, calculating the distance of each tile from its goal state. So for example, for 1 should be here, right? So we should move it 1 to the top. So it's 1, 2 is 1, 3 is 0, 4 is 0, and then 5 is 0 because it's in the correct position. How about 6? What is the distance of 6?
1.
Yup, 6 is 1 because it should be here. 7, 0, right? And so what about 8? 1, 2, or 1, 2 plus 2, and then you calculate the total heuristic by the total, which is 5. Okay, so you do the same for all the tiles, and then you say, okay, from the initial state here now, I wanna, if you wanna like move the tiles, you have like 3 directions, which gives you like these 3 states. Now, if you move, for example, 7 to the right, you reach to this state. If you move, for example, 5 to the left, you reach this state. And if you move 6 down, you reach to this state, right? Now, if you move 7 to the left at this state, what is your heuristic? And sorry, I'm in the slides of the A star search, so that's why the numbers didn't match, and no one actually complained. That's interesting. So we're doing A star search, and you didn't ask me what heuristic I'm using here. So in this example here, the heuristic is number of misplaced tiles, but you can do it, the A star search, with also the Manhattan distance, right? So for like simplicity, and also I already provided 2 examples of Manhattan distance. So for this one, A star search, I'm using heuristic as number of misplaced tiles. So this is your initial state, this is your goal. So heuristic is here is 4 because we calculated heuristic as the total number of misplaced tiles. If you were doing it using Manhattan distance, then your heuristic here was 5. Okay? And then what is G here? Why is G 0?
It's the depth of our tree.
Yeah, so G is depth here. So G in general is your cost from the initial state to where you are now, okay? So in the context of, for example, 8 puzzle, you can consider it as a depth, right? Now, here at the initial state, depth is 0. Here, if you see the blue ones, I marked them in blue. So they are all have like the same G because they are all at depth 1. Now, for the heuristic, again, as I mentioned, here we use number of misplaced tiles. For example, for this one, we have 5 tiles that are misplaced compared to the goal state, right? Here we have 3 tiles that are misplaced compared to the goal state. And here again, we have 5 tiles misplaced compared to the goal state. And also for all of them, G is 1 because we are at depth 1. And the total cost will be the sum of G plus H, right?
So
Yes?
G, is that the cost from any given state to the root?
No. So that is H star. So H, which is the heuristic, is the estimated cost from where you are now to the goal. Okay. For example, you start from Montreal, go to Toronto, and then go to Vancouver. Okay. So the cost, for example, from Vancouver to Toronto, right? If you are currently in Toronto, let's say, if you are here, and your starting point was, for example, Vancouver, then the actual cost from Vancouver to Toronto, because we're already here, so we know what was the actual cost, right? So that is the G. But your estimation from where you are to the goal, so you have some estimation. So you are here, you may have several paths, so you have some estimation of the cost to reach to the goal state. That estimation from where you are to the goal state is H. Now what A star does, and that is the advantage of A star to the greedy best first search, is that greedy best first just prioritize based on heuristic, that is based on this part. So at each state where you are at greedy best first search, it just prioritizes those that have lowest estimated cost to the goal because it only wants to reach to the goal faster. But the problem is it didn't consider what was the goal from the initial point to where you are now, okay? And so in that case, this amount is your total cost in A star. Now, so if you want to like calculate, for example, F for each state, you just add the heuristic, which is 5. Here was calculated based on number of misplaced tiles, plus the depth, which is here the total cost from initial state to where we are now. So for G for all of them is 1. You calculate the heuristic and you end up with the total cost. So which one has the lowest cost? This one, right? So you expand this one. Now you reach to here. So we were here and we had 4 moves, but actually one of the moves were just repeating a state, so we didn't put it here. So if you move 1 to the right, you reach here. If you move, for example, 8 down, you reach here. And then if you move 4 to the left, you reach here. We could also move 6 up, but if you check here, we already visited this state, right? So we didn't move 6 here because it was already visited. Now you calculate heuristic and also the cost of G for each. So for G, like here is very easy because at like each depth that you go further, you just increase G by 1, right, in the 8 puzzle. So now we went to depth 2, so G is 2 for all of them. Heuristic here is number of misplaced tiles, which I marked with red. So this is 3 with this one, 3 for this one, and 4 for this one. So the red ones are the tiles that are misplaced compared to the goal state. And so you can calculate the total cost by adding the heuristic and G, which gives you again the total cost here, F. Now we reach to the point where we have 2 states with the same total cost. Which one do you choose? So both of them, right? So we'll expand both of them because they both have the lowest cost. So we expand this one and this one. The same way we continue. So calculating heuristic, and then you increase depth, that is G is 3 here for all of them. And so we reach to the point that we have, for example, this one as the lowest cost, lowest total cost. You don't have any question up to here, right? I don't go into details anymore. And then because from here, we could move like have 2 moves, moving 1 up or moving 2 left. So moving 2 left is causing like the state that we have already visited, so we don't do that. We can only move 1 up, which gives us this state. we calculate the heuristic, which is number of misplaced tiles, that is 8 here. G, which is 4, because that's the depth that we increase, the depth 1. And then the total cost, which is 5. Now, we only have one state. So is it a goal node? So at each state, you compare if you have reached the goal node. Is it a goal? Your goal state is here. Is this a goal state? No, it is not. So we still have to expand. We have 3 moves here. One of them was repetitive, so we already visited, so we only include these 2 ones. So if we move 8, for example, to the left, or for example 7 to up, if you move 1 down, doesn't matter because we already visited, right? And then you have like these 2 states here. Again, you calculate heuristic, G, which is the depth, and the total cost. And so this one is 5, this one is 7. So you choose this one, but you also have to ask before expanding, did you reach to the goal state? Yes, we are at the goal state, so we don't need to expand any further. So, yeah.
So, how in this question, like with the A star, how the heuristic was same and then.
Sorry?
So we expanded both the paths, right? When we had
Yeah,
heuristic was same.
like this one.
Yeah. So is it the same case when we're doing just Manhattan or just the misplaced tiles?
Yeah, so Manhattan or misplaced tiles is only defining your method of heuristic, right? So, but the whole algorithm for A star is still the same, right? Now, give you 5 minutes and maybe less until 3:30, and then we'll do a Kahoot game together.